Now let's start talking about some acid derivatives. So you have carboxylic acids, and then you have derivatives. These are groups that you replace the OH group with something else. Okay, so it's a group bonded to the acyl carbon that determines the class of carbons. Okay, so first of all, let's first talk about what the acyl group is. So we have, all right, this is the acyl group. All right, so depending on what you change X to, okay, will determine what acid derivative it is. Okay, if it's an OH group, it's a carboxylic acid. Okay. If it's a chlorine, it's an acid chloride. All right. If it's an OR group, it's an ester. And all I'm doing is changing this group right here, keeping everything else the same. All right. If it's a nitrogen, it's an amide. Now, it doesn't have to be two hydrogens. You can have two hydrogens. These are all the possibilities. You have a hydrogen or an R group, or you can have two R groups. And that would be an amide. Excuse me, I had to put on pause because I sneezed. These interconvert via a nucleophilic acyl substitution. We will see a lot of this reaction next chapter. This just kind of introduces it to you. So for example, I can take like an acid chloride, all right? Let's say I could take acid chloride, and if I want to make an ester, I just add that group to it, RO minus, to an acid chloride. And basically it's going to attack and kick out the chlorine, and I make an ester. So these four groups, they're called an acid derivative, and it's a chapter all on its own, because you can interconvert all these things and make all of them. So if I want to make a carboxylic acid, I can start with any of these. If I want to make an acid chloride, you start with this. If I want to make an amide, I can start with the acid chloride. So it's kind of a, you know, you can take one compound and convert it into any of the four compounds. Okay, we're going to kind of introduce it to you here, but I believe we talk more about it in the next chapter. All right, so here's acyl substitution. You take whatever nucleophile you want and you substitute your X group, whatever your X is. If it's a carboxylic acid, the acyl halide, that should not be X, that should be a chlorine. The reason is because the acyl bromide and the acyl iodides do not exist. Only an acyl chloride exists. So that shouldn't even say halide. That's implying they all exist. They don't. It's just an acyl chloride. There's also an anhydride. The last screen did not have an anhydride. It should have. I don't think it did. Did I miss it? No, there's no anhydride there. But the anhydride is one where you have this as your X group. And then you have, you know, the ester, the amide. So carboxylic acids react with nucleophilic acyl substitution, where one nucleophile replaces another on the acyl group. Okay, and like I said, we're going to learn about this next chapter. This is just an example of how you can convert an ester. It's called a basic hydrolysis of an ester. So you can go from an ester to a carboxylic acid. Okay, and basically what happens is the hydroxide attacks, kicks up your pi bond to form, there's this intermediate again, a tetrahedral intermediate. Why is this important? Because you're going from a trigonal planar to a tetrahedral back to a trigonal planar. Okay, so that's why it's just an intermediate. It's a tetrahedral intermediate because it goes from the a trigonal planar back to a trigonal planar through a tetrahedral intermediate. All right, and then your negative charge pops back down and kicks out your OR group. Okay, so that is basically hydrolysis of an ester. Fischer esterification is kind of a very, very common reaction. We did this when we did the banana oil and the wintergreen reaction. Okay, what you're basically doing is you're converting a carboxylic acid into an ester through the Fischer esterification. Okay, so reaction of a carboxylic acid with an alcohol under acidic conditions produces an ester. The reaction is in equilibrium. Okay, so the yield of the ester is not high. You kind of have to drive it. You kind of have to force it. And here you go. To drive the equilibrium towards the product, all right, you use a large excess of your alcohol. remember the Le Chatelier's principle. If you increase one of the reagents, you can drastically drive the reaction. Okay, so in equilibrium reactions, look for ways to use an excess of a reagent or else to remove the products as it forms. Is it possible to use one of the reagents as a solvent? Can you distill off a product or drive off the water? So these are kind of things you have to think about when you're planning out these types of synthesis. Okay, let's talk about the mechanism of the Fischer esterification. We went through this when we did the lab, but let's do it again. First step is protonation of the acid. Okay, remember we're always protonating this because your carbonyl, even though this carbon is partial positive, all right, you want to make this carbon as partial positive as possible. Okay, by protonating it, you're now taking something that's partial positive to something that's really partial positive. This carbon now is extremely partial positive. Okay, in fact, you can draw an equilibrium with this now, which your book kind of does. It's not showing it here, where you can actually have a plus charge on your carbon. Now, I've said in class I don't like that because I don't like to see carbon not octet, but technically it's more like this. So your oxygen is attacking this very positive carbon. All right, so your alcohol now attacks. You have a proton transfer step. Okay, so the alcohol, I actually like to have this protonate, so because you're going to eventually have water leave. Okay, so here's kind of step one where you form what kind of intermediate is this called, guys? Remember, tetrahedral intermediate. Okay, so the carbonyl oxygen is protonated. You can kind of read this on your own. We've kind of already talked about that. Second step is you protonate one of the OHs to form a water molecule. Electrons pop down, kick out the water, and then I would probably have the water grab that to regenerate your acid. But that's basically what happens. It doesn't really matter since you are in a solvent. Since you remember it said your alcohol is your solvent. Since you're in like a trillion times excess of your solvent. Okay, so protonation of the hydroxyl group, it leaves as water. You reform your trigonoplanar, and it kicks it out. All right, here's kind of a problem, kind of a mechanism. You might want to work this on your own before you look at the answer. I'm going to flip through it quickly. I'm not going to talk about it, but you can look at the answer on your own. So you have these three OR groups. In the presence of acid, you can go to a carboxylic acid. So the acid and water is hydrolyzing this off. So using the Fischer esterification example, why don't you see if you can come up with something? Okay, you can imagine your first step is going to be to protonate. All right, one of these might pop down and kick that out. All right, you have a plus charge on your oxygen. Water is going to come in. So see if you can kind of come up with something before you look at the answer. See if you can figure it out. Okay. Esterification using diazomethane. This is kind of a really cool reaction. It's a little unstable because we're using diazomethane. Remember we talked about that diazo compounds are not very stable. What this basically does is it makes a methyl ester. Okay, so your product is always what's called a methyl. Your product is what's called a methyl ester. Why is it a methyl ester? Because that's what you always form. You form an ester with a methyl group attached to your oxygen in every case, because the methyl comes from the CH2. All right. And it's an ester, and you form nitrogen. What happens is nitrogen is a leaving group. Okay, so the carboxylic acids are converted to methyl esters very simply by adding an ethyl solution of diazomethane. The reaction usually produces a quantitative yield of ester, meaning a very high yield. However, diazomethane is toxic, explosive, so not really that fun to use, but very useful. I've used it. It's actually extremely convenient to make an ester. Here's kind of the mechanism. Here is the diazomethane. What happens is the lone pairs on the carbon protonate from the acid, because remember that's acidic. So it protonates to form basically a methyl group with an extremely good leaving group, which is nitrogen. Nitrogen is one of the best leaving groups. So now look what you have. You've got this to easily attack the methyl, and you have nitrogen leave. So that's basically what you have. So it's a very convenient and easy way to make a methyl ester. Amides, very simple to make amides. You basically just take a carboxylic acid and amide and you heat it. Okay, we learned on the amine chapter that amines act as a base. They are basic, so they're going to first deprotonate, okay, to form the ammonium carboxylate salt, and then when you heat it, you form the amide. Okay, very simple reaction. You usually have to heat them. You usually heat the salt. That's, you know, and then it turns into a liquid. Okay. Reductions. Here are reactions with carboxylic acids. You can reduce a carboxylic acid. We've talked about that. LAH, very strong reducing agent to the alcohol. We've also learned that dibal can reduce the carboxylic acids to aldehydes. So you can stop at an aldehyde with dibal. We've learned that. Okay. You can also use borane. We haven't talked much about that. Borane is BH3. It can also reduce carboxylic acids to alcohols. We haven't really talked about that, but borane is actually a pretty good reducing agent as well. We've seen it when we do anti-Markovnikov, when we make an anti-Markovnikov alcohol. All right, here's kind of along the lines of the dibal, but you know, it's this reagent where you take an acid chloride plus a much more mild reducing agent. You could also use dibal as well. That will work as well. That's not dibal, but it's almost equivalent. And you can stop at the aldehyde. Okay, so here's kind of the approach to do it. It's a weaker reducing agent, but it's stronger than sodium borohydride. Okay. We've also learned that if you take dialkyl lithium compounds, you can make the ketone. All right. So remember, two equivalents. The first equivalent plucks this off to form an O negative, and then the second equivalent adds. Okay. Here's the mechanism. First equivalent plucks off the acidic hydrogen. All right, to give you the O minus. The second equivalent adds tetrahedral intermediate. There we go again. When you protonate it, notice you have the hydrated form, which we've learned breaks down into water in the carbonyl. Okay, so you can read that on your own too. Synthesis of acid chlorides, SOCl2. We've seen that. You can also use this compound right here for short, C2O2Cl2. You can use that as well, but we usually use SOCl2. That's kind of the common reagent to make it into a carboxylic acid. They forgot a 2 here. There should be a 2 right there. All right. You always form a gas as a byproduct, so so your compounds are usually pretty clean. All right. Here's the mechanism with the acid with the thionyl chloride. So the carbonyl attacks the sulfur, right, to form this pretty cool intermediate, which is in a resonance form, okay, which can break down. So when it breaks down, you get chlorine, which will pluck that off, to form this type of it's an anhydride. Remember, anhydrides are double bond oxygen, oxygen, and then double bond oxygen. This one has a sulfur though in it, so it's called a chlorosulfite anhydride. Kind of fancy. And then your chlorine comes in, tetrahedral intermediate, and then kicks out SO2 and your chlorine. Kind of a pretty cool mechanism. Why don't you look this over a little bit closer so that you understand how it works. I think it's kind of a neat little mechanism. All right.